All right. First things first. Do you guys have questions from homeworks on the things we've done so far?
Can I ask an overall question?
Yeah, of course.
So for questions like 39, would you know like has a fixed, you can just write that because
Let me pull up 39 so that I'm making sure that I'm looking at the same thing.
he was just asking like something was that
Well, I'm looking at 39 right now, and it's definitely not asking about continuity at point. It wants on an interval. Yeah, so to do something like this for a piecewise function, there's like 3 pieces you need to discuss, right? So I know we know we're continuous from negative infinity to 1 because f of x is equal to x squared there, and x squared is a polynomial. We know f of x is continuous on the interval from negative infinity to 1 bracket because f of x equals square root there, and square root x is radical. And then we need to know really we should probably write it this way. I'm gonna come on. There we go. We need to check if f of x is continuous at the boundary between the two. So to do that, we'll look at the limit as we approach 1 from the left. Well, that's just the limit as x approaches 1 of x squared. So that's 1. And then we need to check the limit as we come from the right. Well, that's the limit as x approaches 1 of square root of x, which is 1. So we know from these two that the limit exists as x approaches 1 of f of x, and that's equal to 1. But the last thing we need for continuity at a point is we need to show that when we evaluate the function at 1, we also get 1, and we do. So this stuff together tells us so we have continuity from negative infinity to 1, we have continuity at 1, and we have continuity from 1 to positive infinity. That's just the whole shebang. So yes, you can use the fact, to get the interval, because you have a polynomial or a radical or a trig function or whatever. But the boundaries between them, you need to check that as a point. You need to check the continuity at a point, the boundary between each piece. Because just because the two pieces are continuous doesn't mean they're going to hook together at that point to still be continuous. Does that feel okay? So again, yeah, like what I did, I didn't prove any continuity over those intervals. I just quoted what I knew, right? I recognized the function type, and that's perfectly appropriate. Like the AP will do that as well. When you need to show, if you need to show some function is continuous to use another theorem, you can just say, oh, this polynomial function, or it's a sum of sum of continuous functions, so I know it's continuous.
Oh, okay.
You know, like you can say things like that and it's fine. You can just say it in words. You don't have to do anything. Here, though, you do need to check the boundaries between your intervals,
Okay.
or boundaries between your pieces, to make sure that the pieces are hooking together and they're not like a jump.
Okay. So how would you know?
So as soon as I have a piecewise function,
What's that?
something like this, where it's defined as like, okay, for these x's do this, but for those x's do that,
Okay.
right? Which is what this is saying,
Okay.
right? It says when x is less than 1, we do x squared. When it's greater than or equal to 1, we do square root x. So that's what we mean by a piecewise function. So like this piecewise function has two pieces. What we have to worry about is where they transition from one piece to the other, making sure that those two pieces, like the one starts where the other one ends. Because if they don't, you don't have continuity, right? You'd have like a jump discontinuity or something there. Does that? Okay. Jacob.
If it's square root of x if x is greater or equal to 1, why do you have to prove it at the point if it's a continuous?
Because so like square root x by itself is continuous here because there is no part of your function defined left, because the domain of this is 0 to positive infinity, right? So like that you can say, but because it's a piecewise function, there is part of it, there is still stuff to the left of 1. We don't know if it's hooking in or not, right?
Oh, okay.
So because that's, you know what I'm saying? Like,
Yeah.
yes, all of that is in the domain of square root of x. However, we're not talking about the square root of x. We're talking about f of x, the domain for f of x, which is the piecewise function. So I can't just assume that starting point is in my domain because I don't know what's happening before it, if it's actually f of x is feeding in or not. Does that make sense?
Yeah.
Yes.
So it's that, again, those transition points have to be checked individually. You can't just theorem your way past them. Does that feel okay?
Yeah.
Yes.
Isabel?
So is it only like in just continuity if like the points for each like function like start or leave off and start or like have two different x values?
You mean y values, right? Because these have the same x.
But like say, if they're like same x value just different y.
Yes, that's a jump.
That's so weird because I was like practicing yesterday and there was one exactly like that and they said it was like something continuous. And I didn't get it.
Well, it would have been like, you would have had something like this, where it like did that, where it filled in.
There were like two separate ones and they're like one was here, one was here. And they're both open simple. It was all like AP class for me. And they said it was still continuous, and then I just didn't get it because it was like a jump.
Something was wrong then, because that's not. Now you might argue like, you could have something like this that's continuous from the right. You could still call that something, or continuous over like some part of the interval. But if the function looks like this, it's not continuous over the entire domain.
Would it be continuous if like one of those dots or one of those points were like filled in?
It's still not continuous over the entire domain if you have a jump. You could say like, if I look at this as an individual function, that can be continuous.
Yeah.
If I look at this as an individual function, that could be continuous. But if they're two pieces of one function, they cannot be continuous. The function cannot be continuous if it has more than one piece to it. Right? Prater, what's up? Shh. Okay, Pierce. Sure. $21. Oh, come on, you stupid thing. So the directions here say explain why the function is discontinuous at the given number a and to sketch the graph. So to show discontinuity, what we would need to show is the limit as x approaches 0 of f of x does not equal f of 0. That's what we want to show. Cool with that?
You chose f of 0 because
Well, it's telling us this is the point that I want to show the discontinuity at. Yes. Okay. So to do the limit as x approaches 0 of f of x, I really have to do, since 0 is a boundary, I have to look at the left-hand limit and the right-hand limit separately and make sure that those are equal. So the limit as x approaches 0 from the left is just the limit as x approaches 0 of cosine x. That's continuous, so that's just cosine of 0, which is just 1. And this, the limit as it goes from the right, is just the limit as x approaches 0 of 1 minus x squared. Again, that's continuous, so I can direct substitute. I get 1 there. So I can say the limit as x approaches 0 of f of x is 1. But that's not equal to 0, which is what f of 0 is. And that's what I needed to show right here. Is that okay, Pierce? Yeah. So if I were to graph this thing then, what would this look like? So I know, like, let's say this is 1, you know, like the right half looks like this. That's open though. That's closed. And then from here, that's a parabola. So it's going to look kind of like this. And I can see clearly like a discontinuity here. So not surprising, right, that it's a discontinuity. The question is just how do I show it? And I'm using the definition of continuity at a point to show that I don't have that. Sure, of course. All right. Anybody else here on questions? We can always circle back if you come across something later, if you didn't have a chance to finish the whole set or whatever. Okay. Okay. Let's do it. This is a very individual question. Let's do it. Let's handle it at the end. We'll have time. I just don't want to you know. But I'm happy to take a look and look at it and talk through it and figure out what's going on. All right. We need to finish 2.5 today. So on 2.5, we've been talking about continuity. Right? Okay. So example, continuing on, here we're asked to evaluate the limit as x approaches pi of sine x over 2 plus cosine x. What would I want to do here for this? X approaches pi. So what I look at here is I want to know if I can do direct substitution on this. Okay, what do I need to have to be able to do direct substitution? Well, what did we also had last time that I could do that with anything that was continuous, right? So as long as I had continuity, I can do a direct substitution because by the definition of continuity, the limit is equal to the direct substitution, right? So what I want to check is to see if this is continuous. So is the numerator continuous? Yes, sine and cosine are continuous. Is the denominator continuous? Yes, because 2 is a polynomial and cosine is continuous. Continuous plus continuous is continuous. Is the quotient of two continuous functions continuous? Everywhere where the denominator is not 0. Can 2 plus cosine x ever equal 0? No, why not? Great, because the lowest value cosine x can take is -1. 2 plus -1 will never get to 0, right? So we're good. This is continuous everywhere. Everybody agree?
Yeah.
As a result, all I need to do now is substitute in. All right, here's the part everybody groans about. AP does expect you to know this. What is the sine of pi? 0.
Is that close?
Sine of, or cosine of pi?
0.
-1.
Okay, so basically I need to put brush up on it.
I mean, the way the quadrantal stuff is easy if you remember that, like, this is sine, right? So 0, pi over 2, pi, 3 pi over 2, 2 pi. And then cosine is, I should try to do it like this. So 1, 0, or I'm sorry, 0, pi over 2, pi, 3 pi over 2, 2 pi. You just kind of think about what the graphs look like. It's easy to do the quadrantal ones because everything is just like a half a pi across. All the majors, like the zeros and extrema. That's the way I think about it, is I just remember what the picture looks like, and then just like, what is it? Okay, it's that. Okay. Yes, Rita.
Like, why did you say, like, it's like you can do direct substitution if, like, anything's continuous?
If your function is continuous,
You can do
direct substitution.
Okay, gotcha.
Yes, that is a natural consequence of our definition for continuity at a point.
Sounds good.
And I should say even better, Rita, is that you don't even need continuity over the entire function. Continuity at the point would even be enough to do direct substitution.
So, like,
But that's much harder to just look at it and tell if you have continuity at a point, right? It's much easier just to, like, the whole thing is continuous. So of course I have continuity at this point.
oh, you mean like continuity, like pi for like this?
Yes, yeah. So if you just have enough to say continuity at pi, you could do it. But that's a lot harder to tell just by looking at the equation, right? But I can tell if the whole thing is continuous pretty easily just by knowing what the stuff is continuous, and like any normal operation of continuous things is still continuous, provided you don't get a zero denominator.
Thank you.
Yeah. And again, that's a super powerful result, right? That simplifies things enormously.
Yeah.
Because now direct substitution is open to all kinds of stuff that we couldn't do before. And these limit laws now become kind of a little more obsolete for us. We still need to break them out every once in a while, but like using direct substitution becomes like our major tool. But we do need continuity to do it. Yes.
So, like, in this lesson, obviously we're doing like continuity, but like
Mhm.
in like the previous like lessons, like there's like other laws that like ways we can like do the same thing,
Mhm.
or like this, like
Yeah.
evaluate. It's like on a test, like will it like distinguish like you? So we could just like use continuity every single time.
Yeah.
So we kind of just like disregard the other stuff in a way.
Well, those things still come up because if you have something that's not continuous,
Right.
you still need those pieces.
That's true.
But yes, you can use problems that we did before. This opens up a new, easier route for many of them.
Sounds good.
So that's the way I'm going to answer it. You can't disregard the stuff we've done before because you still need that. Particularly, I can give you like just the pictures of two graphs or a picture of a graph where continuity doesn't happen and no longer can you do that kind of thing. But you can still do your limit laws.
Right.
So, and for sure you'll see stuff like that on on our test that we'll take for this chapter as well as like an AP exam. Okay. Even better, here we go. If f is continuous at b, and the limit of, as x approaches a, of g of x is equal to b, then the limit as x approaches a of f of g of x is equal to f of b. In other words, we can push that limit inside of the composition. Now be careful here. In order to do this, what must we have?
Continuity.
Continuity specifically on the outer function at the limit of the inner function. If you don't have that, this does not work. Now you will see specifically, like we'll do I have a bonus page here of 2-5 problems where we're going to work on this. Where, like, what do you do if it doesn't? Because the textbook doesn't directly address this. But we'll look at some more examples of this here at the end. Okay. But that's a handy one. So here's an example. Here we have the limit as x approaches 1 of arc sine of 1 minus root x over 1 minus x. This is a composition of two functions, right? We have that rational function inside of the arc sine function. So the first thing I'm going to do is I'm going to check the limit as x approaches 1 of this piece. Okay? Because I need to know what that limit is to see if arc sine is going to be continuous at. For what values is arc sine defined on? Nope. -1 to 1, right? Arc sine is sine inverse, so the possible outputs of sine are the possible inputs for sine inverse. So if this isn't between -1 and 1, I can't do a direct substitution here, is basically what we're saying. I can't push that limit inside of the sine. I'd have to do this a different way. Okay. So how do I do this limit? If I try to do direct substitution here, I end up with 0 over 0. I could multiply by the conjugate. There's an easier way to look at this, though. You can't just square things willy-nilly.
Oh, yeah.
This is the trick that I would employ. When I look at that denominator, I would look at it as 1 squared minus the square root of x squared. Everybody agree that 1 minus x is the same as 1 squared minus the square root of x squared?
Wait, so then do you still have a limit as x
Oh,
approaches 1?
yeah, I forgot to write the 1 there. Everybody agree that I can do that? No big deal. And now what does that denominator look like to you guys? Something squared minus something squared. What is that, Tessa? Difference of two squares, right? Can we factor something like that? Yes. What would that denominator factor to? 1 minus root x, 1 plus root x. Now, if you had chosen to multiply by the conjugate here, that'll be fine. That'll still work. This, to me, I like this because it feels neater, like I don't get anything messy. And now I can just direct substitute. So I get a half. Good. I can do that then. So this then is just going to be arc sine of 1/2. All right. It's unit circle time. What is arc sine of 1/2? Brader. Okay, go ahead.
How did you return the denominator into 1 squared minus square x?
Well, 1 is the same thing as 1 squared, right? X is the same thing as the square root of x squared, right?
Yeah.
So I didn't do any, I just wrote it. I'm like, those are still the same things. I didn't do anything there. I just like made an observation. Yeah, it's a sneaky one, right? You could multiply by the conjugate and it'll work. It's a little messier, I think, algebraically, but it'll work. You'll end up at the same spot. I like factoring. When I see something like that, it's like, oh yeah, it's just a difference of 2 squares down there. Just a little reducey done. So this is one that, like, again, the AP would expect that you could do this by memorization. So it's either going to be pi over 3 or pi over 2, right? Which one?
Pi over 3.
I'm sorry, pi over 3 or 2 pi over 3, excuse me.
Pi over
2 pi over 3.
So again, if you're not sure, here's what I would be thinking about. I'd be thinking about the graph, right? So sine looks like this. 1/2 is here. So this is like pi over 2. So you're something between 0 and pi over 2. That's pi over 3 rather than 2 pi over 3, right? How did I get pi over 3? Oh, I'm sorry. That's not pi over 3. That's pi over... Stupid Mr. Kulik. Okay. So it wasn't pi over 3 and 2 pi over 3. It's pi over 6 and pi over 3. Those are the two that I should be thinking of.
Oh, pi over 3.
Yeah.
Pi over 6.
Yeah, it should be pi over 6. My apologies.
Oh, because sine is y.
Wait, because like, aren't sines just the sines, right?
Yes. Arc sine is the same as sine inverse. Yes. If you type it in your calculator, you can try it. Put it in degree mode, because what is pi over 6 equivalent in degrees? 30. 30 degrees is the same as pi over 6, right? Your unit circle angles, 0, 30, 45, 60, 90, and then multiples of those, right? Okay. So again, just a memorization piece, I know.
Wait, so even though it says arc sine of 1/2, you're really just looking for where sine is equal to positive 1/2.
You're looking at what input, yes, where sine is equal to positive 1/2. Yes. Okay.
Well, that's your
Why
answer.
would it pi over 6 and not 5 pi over 6?
Because okay. So Rita asks, why is it pi over 6 and not 5 pi over 6? Does anybody remember the answer to this? We did it last year.
Oh,
Because that's
has to be.
The range for sine inverse is negative pi over 2 to positive pi over 2. So the only outputs you can get from sine inverse or arc sine have to be between negative pi over 2 and positive pi over 2.
Okay.
That's the same thing for arctangent, but for arc cosine, it's 0 to pi.
I forgot like all the units.
Is there a sheet like with all the songs from like
Yeah,
stuff?
can you like have one of those?
I'll do that after class.
I feel like I just
Like I was like, I feel like
Yeah.
it's like rocks behind the tree.
All right.
I was just like, hey, this is probably gonna be useful if ever gets from.
So the next result here, it says if g of x is continuous at a and f is continuous at g of a, then the composition of f composed g is also continuous at a. Which is exactly what you'd be using if you're doing this graphically, right? So what this is saying is that, like, you know, yeah, we'll do it in a second. We'll do it in a second when I do my bonus content or my bonus examples. All right. So, example 9 is asking, where are these functions continuous? So this is like what we have here, right? Our f of x is sine x, and our g of x is x squared, right? So we're going to start from the inside. Where is x squared continuous? X squared is a
I was
polynomial.
thinking the sign. I was thinking sign.
Okay,
You're right for sign. I mean sign.
it's not right for sine either, though.
What?
That was sine inverse.
Oh.
That's sine inverse. That's okay.
What the heck?
I feel like we need to come up.
I was like, yeah, she's teaching right now.
Okay. Now, if I'm looking at these, how much of that can I plug into sine?
Never mind.
The domain for sine is also all real numbers. Can I plug all real numbers in for sine if the domain is all real numbers? Of course I can.
So they're both
Yes, it's continuous.
I feel like I get it, but I just can't do it because I don't know.
It's so weird.
Shh. Okay. So, again, start by identifying our f and g. F of x is natural log of x. G of x is 1 plus cosine x. If I look at g, where is g continuous?
Everywhere?
Everywhere, right? Because it's the polynomial plus a cosine. Polynomials are continuous everywhere. Cosines are continuous everywhere. Now, where's the natural log continuous?
Nowhere.
Over its entire domain, but what's the domain of the natural log of x? That is incorrect. Okay, 0 to positive infinity. We got to be specific here. What is that 0?
Nothing.
Parenthesis or bracket?
Oh, bracket. Because it can't be low. Oh, parentheses.
Parenthesis.
Wait, what?
Natural log of 0 is undefined. Because if we think about it,
Oh, so it
you'd be
doesn't-
saying 0 equal, or I'm sorry, if I say the natural log of x is equal to 0, I'm sorry, that's not, I want to say natural log of 0 is equal to x, right? What that would mean, it mean e to the x should be equal to 0. What power of e is going to make that 0? What power can I put to e to nothing? Exactly. Right.
That makes sense.
Okay. So, what values? Okay.
So 0.
No. No. So we've identified that it's not going to be a simple plug and play like the previous one, right? So what I need to do is I need to determine where 1 plus cosine outputs values from 0 to pi. Or 0 to infinity, excuse me, 0 to infinity, not pi. So what values of x are going to give me 1 plus cosine outputting things from 0 to positive infinity? Well, now
Or should I not be thinking unit circle?
we will be using the unit circle to do this.
Wait, we want to.
So the only stop talking, please. I'm having to re-explain things because there's too many side conversations going on. So what's going on? We've identified that the natural log, we can only plug in things that are greater than 0.
Yeah.
0 to positive infinity. So the only x's that I can have for the composition are x's where 1 plus cosine gives me things that are greater than 0. Right? The output, the range of 1 plus cosine has to be greater than 0. So let me think about what are the possible outputs of cosine. What are the outputs of cosine? Prater.
So it couldn't be pi, right?
Great. So cosine's outputs are between -1 and 0, right? So the only place we're going to get into trouble is where cosine is equal to -1, because that would make the input for our natural log 0, which we know we can't take. So our function is going to be continuous everywhere except where cosine is equal to -1, which happens at pi as one example, and every 2 pi after that or before that, right? So we could say that we can say cap F is continuous everywhere x does not equal pi plus or minus 2 pi k, where k is an element of the integers. Right? Everybody's okay with that? In between the k and the z, it's just like a soft e. Oh, I usually just draw it as like a 7 and then an opposite 7. That's the symbol for the integers. I think is the easiest way to kind of draw that. You could also just like draw a z and then put like an extra line in there. Either is fine. You okay with how we pieced through that? It's harder, right?
I'm just a little bit confused on the final, like the x, like the pi, plus or minus 2.
Okay. Well, we identified one place where cosine of x is -1, right? And we know on the unit circle, there's only one place where cosine is -1. It's at pi, right? But every 2 pi before or after that would also be -1. So I'm saying, okay, we're continuous everywhere except where x is pi, and every value coterminal to pi,
Okay.
right?
Yeah.
Which is the plus 2 pi k piece.
Okay, that makes sense.
Does that?
Yeah.
Okay. Yeah. Okay. This is the last idea for this section. This is called the intermediate value theorem. This has a name. Do you think it's important?
Yeah.
Yeah, this will be one that you will want to have memorized for the AP exam. It'll be one that you'll want to be able to invoke by name to do free response questions. It may be something that's invoked by name in multiple choice questions. So this one is one that you see a lot. The intermediate value theorem states, suppose that f is continuous on the closed interval from a to b. Let cap n be any number between f of a and f of b, where f of a and f of b are not equal. Then there exists a number c in the open interval from a to b, such that f of c is equal to n. So let's kind of break down what actually I see everyone's pencils moving. Let's pause and let you finish writing what you're writing, and then we'll talk about kind of like what this is saying. Because you read this and maybe it's not super duper clear because it's written in mathematicsese, right? So we need a little bit of a translation, and that's okay. All right. So let's say we have some continuous function. And we have an x value of a and b over which this thing is continuous. Right? Are we continuous from a to b? You betcha. Right? So it's saying then, if I look at the coordinates f of a, or the y values, f of a and f of b, and I pick some number in between that, n, I can find some point on the curve that has that y coordinate, and I can find then its x value that would match to that. So it's saying, if I pick some value between those upper and lower bounds on that interval, I can find an x value in between the domain interval that gives me that specific number. Now, I want to be clear. The intermediate value does not tell you how to find that x value. It simply states that that x value exists. Everybody okay? What is the major requirement for us to invoke the intermediate value theorem is continuity. If you do not have this, you cannot use the intermediate value theorem. Before you invoke the intermediate value theorem in words, you must demonstrate that you have continuity. If you do not do that, you will not get full marks for that problem. You must justify that the hypothesis of the intermediate value theorem is met. You must state that you have continuity before you invoke the theorem by name. Okay? Has to be there. All right. So let's look at an example of how we can use this. It says, show that there is a root of the equation, yada, 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 equal to 0, between x equals 1 and x equals 2. So first thing I'm going to do is I want to show that I have continuity on the closed interval from 1 to 2. How do you think I'm going to do that? No, man. Done.
Oh, you just write.
Yep.
The polynomial.
Yeah, it's a polynomial, man. I have continuity over any interval I want. Done. The continuity is done part is covered. Yes.
What did you write before
I said since.
f(x)?
Yeah, since.
So that, like, since f of x is a polynomial,
It's continuous on that interval.
that's you stated.
Yep, that's just me satisfying the hypotheses for the intermediate value theorem.
You can't just say, like, it's continuous.
You have to say why it's continuous. You have to give a reason.
You said the graph shows that it's.
Nope. Graphs are not proof. Elena.
Most times that we see this, will it be a polynomial?
It'll be something you can do in words.
Okay.
Or it'll be like a sum of two continuous functions. It'll be something like that where it's trivial to do. You just have to make sure you write it down.
Okay, and then like on like the AP test, would this be like a free response? Or do you think they would give us like a multiple choice words?
Well, it might say like, it might give you a situation, say like, which of these do you need in order to say this? And the choices might be like increasing on the interval, differentiable on the interval, continuous on the, it'll be something like, it could be something like that, where they're testing like, do you recognize this in intermediate value theorem and what the what hypothesis you need in order to invoke that. I could foresee a multiple choice question like that. Does that feel okay?
Thank you.
Prater.
What are all sort of all continuous?
Yeah, so we had a list last class. So these are all continuous over their domains, which is good enough for us. Because for a problem like this where we're solving, we're not going to be trying to solve over something that's not in the domain, right? But that's lovely. And then we know that like the sum, difference, product, constant, multiple of, and quotient of continuous things is still continuous. And even the composition of continuous things are still continuous. Like what we just were doing, like plugging one function into another, right? Right here. You just have to be a little bit careful there. Okay, so we're here, right? So what we want to do then is I want to show that there's a value So I want to show that f of x is equal to 0 somewhere on that interval, right? Everybody's okay with the idea? WTS just short for want to show. So I'm just stating what I'm trying to do. So, well, what I'm going to do is I'm going to look at f of 1 and f of 2. And ideally, one of those is going to be a positive number and one of those is going to be a negative number. So if I do f of 1, I get 4 minus 6, that's negative 2, plus 3, that's positive 1, minus 2, that's negative 1. F of 2 is going to be 32 minus 24 plus 6 minus 2, which is what? 38 minus 26, so that's 12.
Usually somewhere on that point or that interval.
That's an interval.
Okay, so somewhere in the interval.
There's a solution, right? There's a value of x where f of x becomes 0 somewhere on that interval.
Oh.
I don't care what the value is actually going to be. We're not going to show that. And in fact, this would be in a no calculator section where you couldn't even like just try to do this graphically and find the intersection. This would be something where we do it in a non-calculator section where you're forced to use intermediate value theorem because you can't actually find it explicitly. Now, what I'll do is I can say, since negative, well, let's just say f of 1, maybe we'll say negative 1 equals f of 1, is less than or equal to n, which was r0, less than or equal to f of 2, which is r12, the intermediate value theorem states there exists a C on the interval 1, 2. Oops. Actually, I think these are supposed to be hard or strictly less thans, such that f of C is equal to 0. So the conditions for the intermediate value theorem. Get it in a second. Okay. We need continuity over the interval that we have. And the y coordinate we're interested in, that being 0, lies somewhere in between two y coordinates on the interval 1, 2, which I've just shown. Because I've shown that, I know somewhere in between those two values of x, there's a point where we cross 0, and that means there's an x coordinate that gives me f of 0, or f of x equals 0, right? If we think about drawing the picture, you know, we have like f of 1 is here, f of 2 is up here. Somewhere, no matter how I draw that, if it's continuous, it has to cross 0 somewhere. There's my point. Do I know it has to cross 0 exactly once? No, right? This could be going crazy, and it could go, and cross a bunch of times. I don't know how many times it's going to cross. I don't know where it's going to cross, but I know it does. That's all I can say with the intermediate value theorem, is that it does. I can't say where. I can't tell you how I'd find it. I can't tell you how many times, but it's there. So Pierce was asking, why do I need to make these bracket or parentheses rather than brackets? And that's, again, just quoting from the intermediate value theorem. So it's just reusing the conditions there. What we're saying is we know that here's why it's parentheses rather than brackets. Because if it was brackets and this was just equal to n, then we're done. Right? If one of the endpoints is 0, then what are we trying to do here? We just did it. We found it. There it is. Right? Isabel.
Like, would there ever be a question where it's like greater than 0, it's like 2 to 12?
Oh,
because in that case it wouldn't, like, there wouldn't be any solution to 0, right?
well, you might have to look at a different value of x then. right? If it's saying to like show that this exists and they give you from 1 to 2 and they're both positive numbers, well, maybe I just have to try a different value of x instead of the endpoints. Maybe I have to do negative a half or I do a half, or I'm sorry, 1.5 or something. And you just have to search till you find like a negative y coordinate, a negative y and a positive. Right? It doesn't have to be over the whole interval. If it's continuous over the whole interval, if I look at a subinterval of that,
Could go like that.
it's still, there you might find what you need elsewhere. That could happen. I would think that would be rare
Yeah.
that they would do something like that, but like if that happened, you just need to try another x. Just have to pick a new x from the interval, until I find a negative one or something. Or if it did, it would probably, instead of saying equal to 0, maybe it had like equal to 5 or something. And then 2 and 12 would be no problem,
Yeah.
right? Because 5 is in between. Does that,
Yeah.
okay. Pierce, what's up?
So, will you ever be given a, like where it says like between 1 and 2, will you ever be given something that'll be like between like 3 and like 8? Like that?
Sure.
So then would you have to do like that process, like f of 3, f of 4, f of 5?
Nope, just f of 3 and f of 8.
Okay.
Ideally,
Because that'll show you where
you just need to find in between,
Okay.
right? You don't need to check every single spot.
Yeah.
You just need to check in between the ends,
Okay.
And then you knew that
typically.
it worked because one was negative and one was positive.
And 0's in between. Mhm. Because 0 is the number we were looking for, right? 0 is the y that we were interested in.
So it could be something different and then you'd be looking for that. Like,
Sure, yeah, if it said equals to 7,
Yeah.
that would still work in this case because
Right.
negative 1 is less than 7, which is less than 12.
Okay.
It works.
That makes sense. Wait, what if it was 7 and it was like 5 and 12? Would it still work or no? Because,
If is 7 between 5 and 12?
yeah, but it's.
Great, then it works.
Okay. Oh, sorry.
Okay. So I want to do some bonus composition of two, or limit of compositions here, because this can be a little bit tricky. So if I look here, I just have a bunch of examples. We're just going to do some examples where we're given graphs rather than functions. So if I look here at f of x, what do I notice?
But it keeps like.
It's continuous. If I look at h, what do I notice? It's continuous. So here, I should just be able to do that, right?
You just put the limit in.
And since h is continuous, I can just do a direct substitution, which should just be f of 1. So I go here and I read that f of 1 is 1.
Okay, that makes sense.
Okay? So far, so good?
Wait, so because you get, when you plug in -2 for the h value, or for the h graph,
Mhm.
you get 1
Mm-hmm.
for the y value, plug that y value into f of x, and that's what gets you.
Mm-hmm.
Okay.
Okay. Let's try another.
Oh no, it's not continuous.
Yeah. All right. What do we notice here about f of x?
Oh, it's continuous.
Continuous. H of x? Okay. So if I look here, that still might not be a problem, because I just need continuity at the point to be able to do the substitution. But what happens if I try to do the limit as x approaches 0 of h? I don't have continuity, right? And in fact, what is the limit as x approaches 0 of h? Does not exist. So what am I going to say here? Yeah.
Yay! Wait, that's my favorite.
Yep.
It's just 5 questions.
Yeah, you can totally do that.
If there's any sort of discontinuity, automatically.
I'm just ready to know.
Alright, that's not doing it. Bye.
Okay. Let's take a look at this one. Let's look at this one. Again, if I look at G, what do I notice? Continuous. If I look at H, what do you notice? Not continuous. Potential problem, right? But if I look, what do I, at -3, what's happening? Does the limit of exist for h of x at -3?
Yes.
Yes. So I think we're okay.
So would you use, yeah.
And then G is 0.
So that limit is 3. And g of 3 is 1.
This feels too easy. Yeah, I feel like when I do it by myself, I'm gonna get really confused.
You haven't seen the hard one yet.
Wait, how come we didn't use the bottom circle?
What's up?
Wait, how come we didn't use the bottom circle?
Because that's not how you do a limit, right?
Yeah.
So we're looking at the limit of h of x.
Oh yeah, because yeah.
And it's okay that I did that because g is continuous everywhere. So as long as the limit for h of x exists, I can plug that number into g and it's going to be fine. I didn't need continuity so much on the h part because I still had the limit existing there. But as soon as I see discontinuity, my antenna's got to go up a little bit, but it doesn't mean that it doesn't work. Let's try this one. What do we notice here about H? And G, which means it's not continuous. Okay, so we've seen though that maybe that's not a problem. What if I try to do, let's look at the limit of g of x at -1. What do we see? Okay, what's the limit though? Very good. Who in the back? Prater? Why doesn't it exist?
Because one's going to positive and
Yep. Yep. The left-hand limit and the right-hand limit are different. So if that limit at g of x doesn't exist, I can't very well plug it into h of x.
What if they both go down to negative?
Yep, you could do it.
So
Would you plug it?
Well, you'd have yes, but on this one it wouldn't make sense. You'd want something. It'd have to be something with an asymptote at that end, where it would be going to a value. But here it's just going straight down, so you just say it goes to -infinity. Also, it looks like. But I would find it unlikely you'd get that with a graph like this. Okay, oops, this one's a little small for my likings. Oops, and I typed that in wrong. Okay. Yeah, let's do that. That's fun. Oops. That's not how I meant it. It needs to be like that. Okay. All right. These ones are the tricky ones. So tune in. This is the tricky one. This is the one where we're going to try to trick you. All right. So what do you notice when I look at the graph of f? Not continuous. Got to be careful. Okay. If I go and I look at the limit as f approaches 0, any problem there? No, right? I notice that the limit as x approaches 0 of f of x is just what? 2. Right? Now when I do f of 2, what do I get?
can't you just use
1.
Yeah, it doesn't exist because it doesn't.
one? But you can use one.
Right, you use 1. Oh, because it's closer.
But it's still there.
Guess what? That's wrong.
Oh.
Why? So why is there a problem? We have the discontinuity at
Same
the point we're trying to plug in. So it's not that simple.
Wait, what?
Didn't we like just do that?
No.
No, we did it where it was like a closer to
But it wasn't a line.
So what you saw is one like this, where we use the limit here. That was fine. And then the value we plugged in was not at a discontinuity, right? You can't plug a limit into a place where you have a discontinuity, at least the way you'd think. So this one is still possible to do, but we have to think about it a little bit harder. So look at what's happening as we're coming into 2. What direction are we going to be approaching 2 from? From below, right? Because 2 is at like a maximum there. So this limit of f of x is going to be the limit as x approaches 2 from below of just f of x.
Wait, what?
So if I look at how we're getting to 2, this is the limit as x approaches 0 of f of x, right? That's heading to 2, but it's always heading to 2 from below, right?
We have to use that point, why was the other one square?
Well, it's x approaches 0.
Oh, I did not see that.
Sorry.
No, you're good, that's on you.
Okay. So what is the limit as x approaches 2 from the left of f of x?
2.
Just does
What? 0.
Right?
No, it's a jump. A full and a jump.
It's that limit, right? It's the left-hand limit at x equals 2.
Oh, yeah, only the left.
Oh, so wait, what? Yeah.
So I get the first part.
Okay.
I have like one quick question. So like backtracking a little bit to what we talked about before. If like the closed circle above 2, I think, if that wasn't like a line, it was just like f of 2, then could you do it? Okay, so in f of 2, like if it was just a closed circle, there was no line following it, right?
No.
Can we do it?
No. Still equally problematic.
Wait, so it only work if you had like.
It's like in the middle of a line and then.
If this was continuous here, it would be fine. But because you have a discontinuity where you're trying to plug your value in, you can't do it the way you think you'd want to do it. It has to be different. Okay? Crater. Okay?
So like the closed circle.
So-
is that like x equals 3 instead? Oh wait, no, that wouldn't help.
No, if the open circle was at like 1, and the closed circle was above 1, then we could do it, right? Because it's continuous. It's continuous at 1. It's not like it's
If it was like the previous example, where you have continuity at the point for the outer function, then yes, everything is fine.
It was just like to be continuous. Like,
Shh. Okay. Let's look at the next one. So we'll start the same way, right? We notice that this is a composition of 2 functions that are discontinuous, so we have to be careful. Let's look at the limit of the inner. What does that look like it is? 2, right? However, if I try to do f of 2, can't do that because that's where the discontinuity is. So what I would want to do is go back and look at how we're approaching 2. So here, we approach 2 from below, and we approach 2 from above, right? So if I do that, when I approach 2 from below, I get 4. When I approach it from above, I get 1. What does this tell me?
Does not exist.
Because the left hand and right hand limits disagree.
Can we go back to this up one?
Yes.
Oh, because the point was the peak, right?
Yes. Yes, because we're always approaching 2 from below. So we didn't have to worry about from the left and to the right because 2 is a Y, right? So
Can you write that down? Because when I did my homework,
this is all in the notes. And I don't know how to physically write this down. This is why I just went and did some examples. Because this is tricky, right?
Yeah.
This is subtle, and you have to like look at the practice. But like I've seen this pop up on the AP, and I've sat there and looked at it like, how in the devil do they get? And I have to sit and think. Okay, now I see it. Because our textbook doesn't have any practice that reflects this. Okay.
Can you slow down? I just want to see like the section. Okay,
Wait, I get the second one, but I don't get the first one.
4. Okay. Wait, where's 4 coming?
Okay, when I approach from the right, it's this point, which is at 4.
Okay.
When I approach from the right, it's this point, which is at 1. And they're not the same value, so the limit doesn't exist. Exactly. Here.
Like for this, like.
Yeah, these are the hardest situations for like a composition of limit of compositions. Is something like this, where it's like, and this is a classic, like a classic no calculator problem, right? Like this is hard without a calculator. Hard enough without a calculator. You don't need a calculator to do it, right? Everything you need is right there.
And do we have to do a little task quiz on Tuesday or no?
We still have 2.6 to talk about.
I was wondering.
I wasn't planning on anything.
Oh.
I still want to talk about those multiple choice questions, but I guess that's not going to be today, and that's okay. No, you're fine. It's totally fine.
Wait, no test next week, right? It would be like
Maybe the week after.
That's shh. Calm down. Everybody's just like bombing questions at me, and it's like I can't even answer before someone's like It's like okay. Almost all of you have had a class with me before, right?
Yes.
And you all know that I'm not an insane person, right?
Yeah. Right.
So like, stop freaking out about the test already, and the test day already. We'll take the test when we're ready. Okay? We still have not even finished all the sections that I want to talk about. We haven't even done any like cumulative practice yet. All we've been doing is individual things. Okay? Just kind of take a deep breath. Okay? Everybody just take a deep breath. If you go into your MyAP, I assigned some more things this morning. You don't have to do anything yet, okay? Because we haven't even finished what I want to talk about for the chapter, okay? And not everything even that I've assigned I'm going to ask you to do, but I can't only assign certain questions out of a multiple choice quiz, or I can't assign certain parts out of a free response question. But you can ignore that stuff for now. Or if you want to start looking at it, that's fine. But don't freak out if there's like, I don't know what the heck that means. It's okay. So today, we finished 2.5. So we have a 2.5 assignment with questions for next week. Okay? Oh yeah, we don't need to, there's nothing new. There's no new questions, right? That's fine. So,
So no homework.
no, yeah, nothing new unless finishing this. So nothing for next week, right? Or nothing for Tuesday next week. We'll talk about those multiple choice questions for sure. We'll try to do 2.6. We'll probably assign some IEP questions also. And then probably the week after for a test.
Yeah, so thank you. Thank you, Mr.
Okay.
Have a good night.
You too.